only 7 attendees.
Hello, everyone. This is John Resso with Wells Darby. We're here live in our makeshift C19 studio here in Warren, New Jersey. We are trying to get away from the norm. It's been almost a year, and I think everybody is kind of like PowerPoint to death. So we've developed a training studio here at our office, and we are going to try and do as much of this as we can live. This is what we call week 1 of our 4-week advanced hydronics. And I will be doing sessions 1 and 3. And Jim DePalma, another one of our teammates here on the contractor services group, will be doing weeks 2 and 4. So it's really important that you participate every week. It's extremely important because what you learn today, and some people on today's conference may already know some of this material, so just please bear with us. I need to make sure that we get everyone up to a level playing field, and everyone will be prepared to go into week 2, 3, and 4. So if some of this is repetitive to you, I apologize, but we just want to take and make sure we get everyone up to a specific level. So it'll be 7 a.m. each day on Wednesday, the next 3 Wednesdays in a row. If you're not familiar with GoToWebinar, we want to interact. We want this to be interactive. There's going to be a lot of emphasis put on you at home doing your work. So lower right-hand side of the screen, you'll see a chat box and a question box. If you need to ask a question, please don't hesitate. Go into the question box, type in your question. We have people in the background that will be answering questions behind the scenes. We also have people in the background that'll be asking the questions live, so everyone will get the answers, which is great, and that's our goal. So who are we? We're Wells Darby. We are a manufacturer's rep. We take and we rep a whole array of heating and cooling products. We're a 45-year-old company, 80-something people strong, with 2 offices, one in New Jersey and one on Long Island. So that's who we are. We do everything from distribution sales all the way up to calling on engineering and teaching engineering classes for continuing education points for engineers. So we cover the whole gamut of scope of work. So in week 1, session 1, we will be talking about the advantages of hydronics. We're going to talk about heat loss. We're not really going to dive into a heat loss class. That would be a whole nother, session. We're going to look at jobs that are going to be a brand new install. We're going to look at jobs that would be a retrofitting a boiler system into an existing home. And because of that, we're going to give you some what to look for, right, and why. We're going to go through some industry terms, just some terms that we're going to cover throughout this course, that we want to make sure that you understand what that terminology is about. And we are going to take and use this setup here and here. And these roll carts are our makeshift boilers, because we can't have a boiler in here. So this roll cart will act as our boiler. And then we're going to go through all the components and why do we put them where they are and what do they do? What's the function of that, that air separator? What's the function of that? So that's what we're going to do in week 1. Session 2, it's going to be very important to pay attention to your emails, and I hope you did for session 1. There were a couple of pages in our TACO catalog that we wanted you to download. It was page 44 and 45. For session 2, some of you may have never touched this before in your career, but we're going to do a system design. So we're going to give you a floor plan, and Jim is going to walk you through that floor plan. So it's going to be very important that you download that floor plan. and have it out there on a piece of paper, maybe a couple of them just in case you need to make some changes. And we're going to design a system. Okay, we're going to make sure you understand how to design a system. We want you to understand from the boiler all the way through the complete heat emitter system back to the boiler and how to control that. We're going to give you the option of cast iron boilers versus condensing boilers. And Jim will take you through that and give you, you're actually going to pick for your system design, whether you want it to be a cast iron type application or a condensing type application. Then he's going to walk us through in week 2 what a typical heat load distribution would be for our footprint, right? He'll go through, you know, how many hours a circulator runs and how we look at the performance of our boiler and how it affects the sizing of our boilers. And if you already know, great. If you don't, you will leave here hopefully understanding and knowing how to size a circulator correctly. Circulators all have what we call performance curves. And when we hook that to a system, like this circulator is hooked to a system, these circulators are hooked to a system, we're going to understand the system curve side of it. So there's 2 different curves that we look at. We look at the circulator curve, the performance of the circulator, and we're going to look at the system curve, and we're going to help you match those 2 up so that you have a proper performing system. And we're delivering the BTU to the home instead of bringing the BTU back to the boiler. That is week 2. In week 3, we're going to review static pressure in a boiler. We're going to go through static pressure. What is it? What does it do? How does it work? What are the components that allow you to adjust static pressure and everything about it? We're going to talk about the position of a circulator within a system. Do we put them on the supply? Do we put them on the return? And we're going to answer the questions of why. Okay. Right here, we just have a typical cast iron type pipe boiler, just direct supply out, return back. We're going to get into primary, secondary piping. So for your condensing modulating boilers, for some larger commercial style boilers, that's primary, secondary piping. That's where we hydraulically separate the boiler system from the heating system so that the circulators don't see each other. And we'll go through how to do that and why it works and some of the nuances of how to make it work properly. Okay, we are going to talk about the age-old battle back and forth. Is it zone valves or is it circulators? And realistically, there's no wrong answer. We all know that, but we will give you just some thoughts as to making a decision whether it should be a zone valve or a circulator system. And then we get into what we call root cause troubleshooting. So again, for session 3, it's very important that you download the information because we are going to put you in a boiler room. We're going to give you the homeowner's problem based on what you learned in week 1, what you applied in week 2. You're going to take both of those and apply them to the root cause troubleshooting that we start in week 3. So if your head hasn't exploded yet, we have more. We have week 4. Week 4, we're going to do a review of weeks 1, 2, and 3. Then we're going to dive into, we'll be talking about boiler systems the whole time. We're going to dive into how do we control them. So we're going to go through the switcher relays, and I think DACO has some really good kept secrets, and we don't want them to be kept secret anymore as to how to apply these switching relays so that you can get the most performance out of the switching relay and the most performance out of your system. Okay, I don't know how many of you know this or not, but Jim will blow your mind in week 4 and tell you that this is a zone valve switching relay, but we can also run a circulator for the indirect hot water heater if they have that. And then again, print out this information because we will be getting into more root cause troubleshooting, and we will put you in that boiler room again, and we're going to have you go through and check out everything in the system, from piping to circulators to flow rates. Everything will be checked out. Our goal as Wells Darby, we want to answer the whys. Okay, When I came into this industry, I was put into a service van with a senior tech, and we went out to every job site and we did everything you could imagine, from installing boilers to troubleshooting, you name it, we did it. And every day I went out there with him, he would say, put here, put this here, put this here. I never knew why I was putting any of that material where I was putting it. So the goal of this class is to answer all those whys. In addition to that, we want to help you understand the formulas used to design and troubleshoot a hydronic system. This is information that we use every single day. This is information that's in the TACO catalog that we sent out to you guys for downloading, page 44, 45. A lot of that information is on those 2 pages. Okay, so this is what our goal is, to make sure you understand how to break out a system, zone by zone, how to break it all out and make sure you understand if there's a problem, how to correct it. And we want you to leave our training with the information you came for. So if we're not hitting on something that's part of the course, or we're not going deep enough into something in our training, we need you to fire us off a question. And if we're going to go down that road, we will. If it's something outside the scope, we'll reach out to you and do it privately. So because this is a 4-week training session, we usually leave an hour or so open, whether it's after a class or during the week. So if someone feels that they're falling behind, they can email us, either jresso@wellsdarby.com, jresso@wellsdarby.com, or Jim DePalma@wellsdarby.com if you need additional help, if you feel like you're falling behind. We want to make sure you're current so that everyone, is up to speed and they're going to get out of this what they came for. So we're going to jump right in here to week 1. Hydronic heat. Why do we sell hydronic systems? Okay, this is a hydronic system. When we talk hydronic systems, we're talking about this roll cart. This is my boiler. I have water in this boiler, and my goal is to heat that water up, send it out of the system, out through my heat emitters, back down through the return piping, back into the boiler to be reheated. So why do we sell hydronics? If anyone wants to shoot off an answer, you got a couple of seconds to do so. Why do we sell hydronics? What's the value of selling hydronics? Well, everyone here today on the course, we sell comfort. All right, that's what we are. We sell comfort. So majority of the companies out there, if you were an oil company, you turned into a comfort type company, right? You're not just oil anymore. If you were, just doing gas or whatever you want to call it, any type of just service only, we have to be a full service company.
Got one answer. Tony Perez, more efficient.
Tony Perez says more efficient. Okay, good. We are going to get into that. We're going to cover that. So that's great. So some of the main advantages in that comfort that we're selling to these homeowners is we provide heat through convection and radiation. Okay, so we're not getting cold within the space. We don't have air blowing across our skin and making us feel cold. So we have, I'll refer to anything that puts heat into the space. I'll be calling it a heat emitter throughout this course, just so you guys are familiar with, my terminology. If it's a piece of baseboard, the heating element inside of that baseboard to me is a heat emitter, right? If it's a Modine heater hanging in the corner of a garage or your shop, that's a heat emitter to me. So because of that, the way we put heat to those heat emitters, it's more comfortable to the body. It limits the heat loss of your body, which makes you feel comfortable within the space, compared to a forced air system where we have greater temperature swings and we just get more comfortable in a radiant heated home, baseboard heated home, anything hydronics. Design flexibility. We can zone. Here we have a 2-zone system. Here we have a 2-zone system. We could design with as many zones as we want. We can go as crazy as we want. If we use these ZVC panels and SR panels, we can go up to 120 zones. Don't ask me why, but we can. So that's where we're at. with zoning. We have another question.
Well, not a question, but Brian. Use over a long distance.
Easier to deliver BTUs over a long distance, right? We're just gonna take a look at the pipe size and make sure we size a circulator to get us the proper head and flow we need to support that BTU. I always joke about improving air quality with hydronic heat, and it's just like it's a talking point. And with COVID-19 going on, if I got a hot air system, I can't isolate like one room within the home because I may, if the system is installed in that space. So any germs that are in that space, I'm going to be taking on and sending them throughout. We lost our camera.
Yeah.
Just volume. I'll just keep going until you get the camera back
Yeah.
on. No
Okay.
problem. We got to turn your camera on, right? Turn your webcam on.
Yeah, click on that.
And if you could, get me the clicker out of Eric's computer and
Yeah.
plug it into mine.
Here, Chris, give this to John.
All right, I got your camera, Jim. That's a good start. So you're gonna stay like right here and type away. So grab someone else's computer for questions. Okay, everyone, we apologize. We had we're not sure really. We had a power outage or something. We lost our whole camera. So we're now working off of a laptop computer. So we apologize for that. Some of the other key advantages when we talk about hydronic heating is the flexibility. We can use one heat source. It'll allow us to do central heating, multiple temperatures, multiple zones. We can do domestic hot water, snow melt, pool heating, you name it. You can go as crazy as you want with a hydronic system. If we're competing against a warm air system, usually you can get a couple of zones that'll work fine, but usually one temperature. Here, we can use mixed valves, use the boiler temperature, adjust it however we want to make sure we can deliver everything that we need to the home. So if we were talking about a new house and you get a call from a builder says, hey, I'm putting up this new house, and I'm still green here.
You're not on here.
Okay, I'm on that. Okay. So we're just working through some technical issues here, so bear with us. So with a new house, here we are. We get a call from a builder. He's got a new house and he wants us to come in and do a heating system for him. We could also possibly be called by a homeowner and say, they got a 30-year-old house and they are looking for a retrofit. And we're going to go into that home and we're going to take a look at it and figure out what we would need to support that home. No matter which type of work you do, or if you do both, it really doesn't matter. Probably the most important thing you could do is a heat loss calculation. And we talked to how we would, just discuss heat load, but we're not going to get into and do a whole training class on heat load. So majority of the people doing like manual J's and different types of heat load calculations, whether it's right soft, manual J, Takeo Flow Pro, we really don't care what brand heat loss calculation you use. We just want you to use one. Majority of the boilers in the Northeast are oversized, and I would say probably 50% of them that are oversized are probably grossly oversized. So go in there, figure out the BTU load of a home, what the energy loss is for that home, right size the boiler so you have a efficient system that's not going to short cycle, and we'll touch on that, and it'll give you the proper performance that you're looking for. So heat load calculations, that's probably one of your best tools, because if your competition does not do a heat load calculation, they may be going in there and just matching a rating plate. So again, whether it's a Takeo, Flow Pro, Right Soft, whichever brand you use, just please do some type of heat load calculation. So if it's a new home and you're dealing directly with the builder or with the homeowner through the builder, heat loss calculation, usually that's done, whether it's an engineer or architect having to do with the new home, you need to understand what those numbers are. And in addition to that, especially if you're working with the homeowner, understand what they're looking for, okay? Figure out what type of heat emitters they want. Is this going to be, maybe radiant in the kitchen and bathrooms for comfort, and maybe baseboard throughout the rest of the home? Is it going to be some type of a air handler type system, because they may want to put a hydronic coil in some type of air handler and have air conditioning at through the same device? So understanding what the homeowner's wants are, what the homeowner's needs are, is very important. And when you're talking with the builder on this brand new house, it's going to be critically important to understand the insulation, the value of the insulation, and what type of insulation is it. Because based on the insulation that may be going into that home, if it's just our typical, R19, R38, R21, whatever it might be in the walls and 38 in the ceiling, that's fine. But when we get into these houses with the new spray foam, that becomes a little more critical to understand, because at that point, we're going to probably have to go down the road of either an HRV or an ERV, so that we can take and exchange air from within the home to the outside to make sure we have a healthy home. If we do not address that fresh air makeup, if it's a brand new home with a poured foundation, this is just something to look for. Go to the windows and look for a little moisture on the bottom side of the window inside of the house. That could be, if it's a poured foundation, that's the moisture coming out of the concrete. And because the house is so tight, we're unable to, remove that moisture that the concrete is putting into the home. So that's where the ERV comes into play, and exchanging that air, with that cross heat exchanger, taking some outside air, putting it across the heat exchanger, taking inside air, putting it across the heat exchanger, expelling that to the outside, bringing in outside air, grabbing the heat molecules and putting it back into the home. So we're flipping the air within that space. That's what these tighter homes need. If you do any commercial work, you know that that's being done every day in a commercial application and or school. But the most critical thing is understanding the homeowner's expectations. If you're going in there to just put in a standard boiler, with a typical 40, 45 gallon indirect storage tank for hot water, domestic hot water, and they put in a 11, 12 gallon a minute human car wash shower, you're obviously not going to meet their expectations. So it's critically important to know exactly what the homeowner is looking for when you go ahead and size up and price out that job. Retrofits. This is where, we see a lot of problems with retrofits. Someone will go in, they'll look at the rating plate on the old boiler and think that that's the right size boiler. Others will go in, they'll measure the heating element within the home. And the rating plate tells you exactly that, the rating of the old boiler. It doesn't tell you that's the right size for the home. It just tells you what the rating plate is on that boiler. Measuring the radiation, that's helpful. It tells you how much radiation is within the home. Is it the right amount of radiation? Is it oversized? Is it undersized? That's critically important, because that plays into your boiler choice. Okay, if I have an abundance of radiation, I may want to go with the condensing type boiler, because now I can reduce water temperatures, which means I will run more efficiently. All right, if it's a gas system, guys will go in and they'll clock the meter. They'll watch the gas meter rotate around, and they'll figure out over 1 minute how many cubic feet of gas went through the meter, and then they'll multiply that by 60, and they'll do it by the hour, and they'll figure out what that boiler burns. That still doesn't size it correctly for the home. That just confirms that the boiler is what it is. If it's an oil boiler, guys may go there and look at the nozzle size and say, okay, if I got a 100 PSI pump and I got a 1 gallon an hour nozzle, it's a 140,000 BTU input boiler. And truly, that is a 140,000 BTU input boiler, but it still doesn't answer the question, is it sized right for the home? All right, other guys, going back to gas, they may check the orifice size and say, okay, I have this orifice size, I have multiple burners, multiply it out and calculate it that way. Really not the way to size a boiler for a retrofit. The best tool in your toolbox when it comes to doing a retrofit on a system is heat loss calculation. Okay, so whatever program you use, that's your best tool. And for a lot of the rebates that are out there, manual J is required. So on that retrofit, this is where you're at the kitchen table with the homeowner and you ask them, have you made changes to the house? And they say, yes, we did windows, we did insulation in the attic, right? So now, as you're doing that manual J, you're going to see those numbers come way down. That will confirm that the old boiler was oversized. Another key feature here, when you go down the basement on an old boiler, it's real important. Pull the cover off the aquastat and look at the operating temperature of the boiler. Okay, we're used to in the oil world, 160 degree low limit, 180 degree high limit, and that's fine. But we want to make sure we look at those temperatures, because if I don't have enough heat emitter within a home, I can elevate the temperature of the boiler, maybe 200, 210, whatever that number is, to get more BTU out of each foot of baseboard within the home, I can do that. If I go and sell that person a condensing modulating boiler, I don't have the ability to get the temperatures on that condensing modulating boiler up that high. Some boilers stop at 176 degrees. So that means I'll never be able to support the heat in that home because they don't have enough heat emitter and I don't have enough temperature within my boiler. So it's critical to check that aquastat to make sure that we can support everything going on in the home. Type of heat emitter is important. Okay, if it's baseboard, if it's radiant, you know, that's a system we can look at and possibly adjust the temperature a little bit, get it off that 180. You know, there's no rule that says everything has to be at 180 degrees. If we can heat the home with lower water temperatures, we can probably install a condensing boiler and give a more efficient system to the homeowner. Okay, so system heat emitters, if I have an air handler in the attic and an air handler in the basement, and I'm going to run that system at 180, 190 degrees all the time, you know, I may not want to propose a condensing modulating piece of equipment because I need a minimum of 130 degree air up to that air handler so I don't blow cold air into the space, or what feels like cold air into the space to the homeowner. System conditions. I always like to look at system conditions, and I'm not necessarily talking about the condition of the baseboard, the condition of what the homeowner sees. I'm talking more about what's inside of the pipe. I want to know what's going on inside of this pipe, especially if I'm going from an old, let's say, cast iron radiator system with a cast iron boiler to a new condensing piece of equipment. I'm going to make sure I want to put, you know, some type of, you know, Taco mag dirt separator on that system on the return before it gets back to the boiler so I don't do damage to the boiler. And then again, homeowner's expectations. Okay, if the homeowner has a pipe going through the floor that's creaking on the third floor when they're making heat, you changing out the boiler is not going to fix that, right? That was the guy that put the pipe in, probably didn't drill a large enough hole, and every time the pipe expands, you hear the creaking. So just make sure they understand that just by changing out the boiler, you're not fixing every problem they've ever had within their home. And when we're doing all this and we, you know, check our BTU load and we want to right size everything, if we just match rating plates and the boiler is oversized, we're going to short cycle the boiler. Anytime we short cycle a boiler, it's going to lead to higher fuel bills. So think of this in your automobile as stop and go traffic. You use more gas if we're stop and go compared to putting your car on cruise control. Let's say on, you know, the New Jersey Turnpike, put your car on cruise control, you'll get better fuel mileage. Same thing goes on in the heating system. When this heating system is running at steady state, that's when it's most efficient. The dirtiest 2 points of a heating system's operation is startup and shutdown. So the better we can make this thing run, the longer cycles we can make it run, the better off we are. So all of this short cycling that's going on will also lead to premature component failures. So I may be going through igniters, I may be going through transformers, I may have some problems where, you know, I'm going through components because I'm short cycling my boiler. That will all lead to higher service and maintenance costs. And that's, we're not putting a new boiler in to have a homeowner spend more money. We're putting a new boiler in hopefully to reduce the cost of operation for that homeowner.
Look this up, just give a second.
Yeah. Okay. Undersizing a boiler. Undersizing a boiler, I'm not telling you here to downsize a boiler so much that it's struggling to heat the home properly. That'll just lead to inadequate heat at or, you know, below design temperature. Could be every day. It depends on the application, but don't undersize a boiler. Don't kill it and oversize a boiler. You know, it's $150 more for another section, right? So I'm going to put another section on. Just right size the boilers and it'll just make everything work better. So if you have that old cast iron type system and you're going to replace it with a condensing boiler. So we talked about a mag dirt separator, and Taco makes a mag dirt separator. It's in your catalog that was shipped out to you. It would go right here on the return before it gets back to the boiler. So we have that. But prior to putting the new boiler in, the best practice would be to flush the system. And there's a couple products out there, and look, we don't sell a cleaner, we don't rep a cleaner, but whether it's Fernox X3 or F3 or Sentinel X400, try to get that into the system. Let it run in the system for a couple of weeks before you change out the piece of equipment, and then drain it, flush it. Every boiler manufacturer will tell you to flush the system with water before you install the new boiler. So you have the opportunity to put that cleaner in there. It'll go in, clean up any dirt and debris that's within the system, flush it out of the system. You'll have a cleaner system. You'll get better heat exchange and deliver BTU much better. So one thing with those cleaners, make sure you read the manufacturer's recommendations, but most of them, you don't want to leave them in more than 30 days. You'll start to lose the ability to grab the dirt and debris and capture it and expel it from the system. You leave it in over 30 days, those particles will start to fall back out and land in the system again. So we're going to get into some terms here, and we're going to start with BTU. And everything in our industry is geared around BTU. BTU is a British thermal unit. That's the amount of energy needed to raise 1 pound of water 1 degree Fahrenheit. That is defined as a BTU. So a BTU is a BTU is a BTU is a BTU. Okay? Doesn't matter if it's coming from a gas boiler, an oil boiler, a wood stove, a candle, a cup of sterno, you name it. If you're producing BTU, then you are putting heat into something. And in our world, everything is geared around a BTU, and we're going to show you how to start applying some of that to the system. GPM, gallons per minute. Gallons per minute. That is extremely important to us because we need to know the flow rate that we're sending out to a heat emitter to make sure that we can deliver the proper BTU to that heat circuit. So gallons per minute, that's going to be a very important one also. And then we have this funny little sign. It's a triangle with a T next to it, delta T. So delta T. So what we're using a delta T for is delta T is going to be a temperature differential. And majority of everything we work with in the hydronic world is geared around a 20-degree delta T. There are some variations, but the most practical number to use is a 20-degree delta T. And we'll go through what that is. Velocity. Velocity is another one that we work with in the hydronic world. We need to control how fast water moves within a pipe. And we'll touch on velocity here in a little bit. AC current. AC current. This is a standard AC current circulator. Okay. This is a 007 AC circulator, and they're great. We have a whole line of AC circulators, alternating current circulators. Just to give you a reference point, this is equal to about an 80-watt light bulb. So when this is running, it's equal to about an 80-watt light bulb. In our footprint, this motor runs about 2,500 run hours a year to heat your home. So that would be like turning on a 80-watt light bulb and leaving it on for 2,500 hours. That will heat your home for the course of the winter. Another term is ECM. Okay, that's electrically commutated motor or DC motor. This is a DC driven motor. There's some advantages. Taco has a whole line of ECM motors. We also have a whole line of AC motors, been around forever. So we're going to touch on both of them and go through some of the differences on those type of circulators. AFUE, you'll see that on the side of every boiler. That's annual fuel utilization efficiency. So every boiler will give you a number. And whether you're dealing with a cast iron product in the mid 80s, low 80s, maybe to the high 80s, or you're dealing with a condensing boiler that may rate it at 95, 96, whatever the number is. Those AFU numbers are done with 140-degree supply water, so 140-degree water leaving the boiler and 120-degree water returning to the boiler. So that's where those AFU numbers come from. If you're not running the boiler at those temperatures, then we may never see the efficiencies that the boiler is rated at. So let's dive into where do we get all this information from. So right now, I am going to be looking to my TACO catalog, and I am going to be looking at page 44. On the upper left-hand side of page 44, it says Universal Hydronic Formula. That Universal Hydronic Formula reads as such. GPM equals BTUH divided by delta T times 500. And I'm no rocket scientist, I can tell you that. But I think it was like maybe 8th grade math. They told us anytime you had parentheses, we're going to do the math within the parentheses first. So I said earlier, our most common delta T is going to be 20. So what I would do is, and I hope you can see this, I would just take under my delta T signal and take it right at 20. And that stands for 20 degrees. Okay, with the 20 degrees right there, that's going to tell me that if I look at a boiler system, I'm just going to remove this camera a little bit here to focus a little more on this boiler system. If I look at a boiler system, this is my supply header right here. When I leave this boiler, I'm going to leave this boiler, I'm going to call it 180 degrees because that's what we're used to talking. I'm going to leave the boiler. I have 2 heat circuits. I'm going to go out to those heat circuits. I'm going to try to deliver the BTU out there to my heat emitters. I'm going to come back into my return, and I'm going to drop back down into the boiler. And the goal is to use up 20 degrees worth of that temperature during that process. And what that allows me to do is that allows me to send that water back to the boiler. The boiler will come on, it will re-energize that water. It'll increase it by 20 degrees based on the flow across the heat exchanger, and I'll send that water out again. So if I need to understand what's going on here is I need to understand that inside of this boiler, I have water. This is a 1-gallon container of water. All right. Based on this 1-gallon container of water, I need to understand how much BTU I can put into this gallon of water, get it out of the boiler, deliver it to the home. So right here we have 500. I'm going to take the 20. I'm going to multiply that by 500, and that's going to equal 10,000. So where does the 500 come from? The 500 comes from a gallon of water weighs 8.33 pounds. I take that and multiply it by 60 minutes within an hour. That's going to give me 499.8 or 498.9. We call it 500. So now I'm putting a number to how much energy this gallon of water can absorb. And by moving it through my system, I now know how much energy I can deliver. So every gallon of water within this system at a 20-degree delta T has the ability to carry 10,000 BTU. And that becomes critically important because that's our medium. Our water is our medium to deliver the energy that we're producing. So gallons per minute equals BTUH. So this is our boiler divided by delta T, 20-degree delta T, entering the boiler, exiting the boiler, 500. So 10,000 BTU, let's say I have a 100,000 BTU boiler, and I'm told here to divide. If I take 10,000, divide it into 100,000, my flow rate is now 10 gallons per minute. Okay, I hope everybody's with me on that. Work some of these. 20-degree delta T, gallon of water has the ability to carry 500 is our number. 20 times 500 is 10,000. I can carry 10,000 BTU with that gallon of water. I can take and divide that into my boiler size. You probably want to do this off of the net number, not off of the gross number. And then that'll give me my flow rate that is expected to be delivered by that boiler, that circulator, that heating system. Knowing this universal hydronic formula is going to be critical. We are going to use this throughout this whole process. This is going to be key for us to understand how we deliver energy to a heating system. So I am now going to just move you over a little bit, and we're going to look at this boiler. Okay, so here's my boiler down here, and it's X amount of BTU. My burner comes on, I start to heat the boiler up. Let's say it's a little cast iron gas boiler, it might hold 4 gallons of water. Okay, so we're going to take 4 to 6 gallons of water, whatever it is. We're going to input, let's say 80,000 BTU. That means we need 8 gallons of flow across the heat exchanger, right? Because I can use this formula in many different ways. So I'm going to take and move 8 gallons a minute out of this pipe, and it's coming out at 180 degrees. My circulator has the ability to move 8 gallons a minute, and I have 2 3/4 heat circuits. 3/4 pipe has the ability to carry 4 gallons a minute each. So there's 8 gallons, right? It's going to go out. This is my first floor, going through my baseboard on my first floor. This is my second floor, and I have pipes going out to my heat emitters. We're going to go out at 180 degrees. It's a design day outside today. It's cold. So we're going to go out through the heat emitters. We're going to come back down through our zone valves, which are in the open position. And the water coming back should be cooler. Let's call it 160 degrees. It goes back into the boiler. This is a cast iron boiler. Goes back into the boiler. The boiler's on, firing, gets the energy, gets injected into the water. The water absorbs the heat energy, pulls it out of the top of the boiler, sends it back out to do that circuit again until we satisfy that heat demand for zone 1 or zone 2, whether it's the upstairs zone or the downstairs zone. So this is how we're going to utilize that universal hydronic formula. So if I know any 2 of the 3 that are there, so if I know gallons per minute, I pretty much have an understanding that I can always use 20 as my delta T, 20 times 500, and my boiler size. So if I know I have a cast iron boiler with baseboard, I know that's a 20-degree delta T. So I know that number is 10,000. If I know the flow rate, I can take the flow rate and the delta T, divide them out, that will, or multiply them, and that will give me my boiler size. And that's going to help me understand if my piping size is correct, if my circulator size is correct, and all of the different systems are working properly. So that's what we're going to use this universal hydronic formula for. And here's a little breakout as to what it would look like. So cast iron boilers, condensing boilers, baseboard, convectors, indirect fired water heaters, plate exchangers can be designed around a 20-degree delta T. Modine hot dog heaters can be designed around a 20-degree delta T. Majority of everything we're working on will have that 20-degree delta T. If you're a big radiant contractor, majority of the radiant we design is around a 10-degree delta T. So if we're designing that, all we would do is look at this 20 right here, and we could change that to a 10, a 20, a 15, a 25, a 30, a 40, and we could change that delta T. So it doesn't matter really what working with, as long as you understand the delta T for that product, we can design a system around it. So when we look at copper pipe, we're looking at 1/2-inch pipe. Let's say we want to know our flow rates and such through the different types of copper. If I look at 1/2-inch with a 20-degree delta T, I can carry 20,000 BTU. And that would be about 2 gallons a minute. If I look at 3/4, like I have right here, which is the most common size we see on the heating side, that will carry about 4 gallons a minute and about 40,000 BTU. Most common size we see on boilers for supply headers and return headers is 1.25 inch. 1.25 at a 20-degree delta T will carry 140,000 BTU. So that's just an idea of, we get called out to job sites all the time, our contractor services group. And we get to the boiler job and we look at it, and let's say I got a 250,000 BTU boiler here. This is 1-inch pipe. I know 1-inch pipe carries about 80,000 BTU at a 20-degree delta T. Now I know why the boiler is short cycling, because this is my choke point. The 1-inch pipe is my choke point. So I'm unable to get the heat energy out of this boiler because my piping is too small. Okay? When you look at a condensing boiler, you may buy a 200,000 BTU condensing boiler, but it only has 1-inch takeoffs. It has 1-inch takeoffs because inside of the jacketed area where they bend the pipes, they can't fit larger diameter pipes. So they calculate that smaller pipe diameter into the head loss of the heat exchanger. So as soon as you leave that heat exchanger and the piping outside of the jacket, you probably want to increase that to handle and support the BTU that the boiler can produce. Same thing with an indirect. An indirect might only have a 1-inch tapping in the side, but the coil inside of it has the ability to absorb, 150, 200, 250,000 BTUs worth of energy. But if you look at a standard pipe chart, 1-inch only carries 80,000 BTU on average. So you say, well, I can pipe it in 1-inch. Well, you can pipe it in 1-inch, but you'll only deliver 80,000 BTU to a heat exchanger that can absorb 150,000 or 200,000 BTU. So it's really important to understand from a manufacturing side that they can't take 1.25 or 1.5 pipe and coil it up the way that they need to and have an 1.5 tapping out of the side of the indirect. They go with 1-inch, but they just put more of it. So you have more surface area within the indirect to absorb that energy and exchange it into the domestic water. So understanding the ability for a pipe to carry BTU is very important. And we need to make sure that our piping is always sized correctly to marry up to our heat load, and that our circulator is sized correctly to deliver the BTU out to the heat emitters that's needed. So just a typical, so we keep our velocities within range. We go 2 to 4 gallons per minute is on average for a 3/4 pipe. We go 4 to 8 gallons a minute for 1-inch pipe. We go 8 to 14 gallons a minute for 1.25 pipe. And we go 12 to 22 gallons per minute for 1.5 pipe. So if I were to say, and I'll grab a marker, if I were to say my gallon per minute is 22, I have a 20-degree delta T, so this becomes 10,000. My question mark is right here. What size is my boiler? So if I take 22 and I use this universal hydronic formula, but this time I'm going to multiply 22 times 10,000. Who can tell me my boiler size? You can fire off, send that in. Give it a second. Getting a couple answers. And we are 220,000 BTU. That would be our boiler size for that type of a system. Okay, so that's really some of the ways we utilize the universal hydronic formula, we make sure that we can deliver the BTU that the boiler is producing through the connected piping system that we're hooking to, and we have a circulator large enough to handle the BTU load and the friction loss within the system, which we refer to as head loss. Our goal in the hydronic world is to have water move within this pipe at somewhere between 2 and 4 feet per second. So if I'm a gallon of water in that heating system and I'm here in 2 to 4 seconds, you know, I can't move too far. I can only move about 2 to 4 feet per second. If I exceed 2 to 4 feet per second and I get upwards of 6 feet per second, I will start to create noise within the system. If I were to exceed 8 feet per second, I will actually start to erode metal within the system. Okay, so our goal in the hydronic world is 2 feet per second. Anything below 2 feet per second, I lose the ability to move air bubbles in a downward pipe. I lose the ability to move the air out of the system, bring it back to the boiler, to the air separator, and expel it from the system. Those air bubbles may end up all getting together and having a party on the 3rd floor and creating a no heat situation because we just created an air pocket on that 3rd floor. So we're running along here. Just wondering if anyone has any questions. If you have a question, type it in and let us know. Jim, you got a few?
Yeah, one is from Ray. He's asking, you know, is there an issue if you have too big of a circulator?
Yes, there can be. And I believe it's going to be week 3. We will start to size circulators and go through why. But just a quick brief overview and an answer right now. Our goal is to deliver a 20-degree delta T. One of the myths in the hydronic world is we want to deliver the hottest boiler temperature and deliver a 20-degree delta T supply to return on the design day. So we happen to be in New Jersey today doing this presentation. Design temperature for this area where I am right now is 14 degrees outside. So if it were 14 degrees outside, I would need 180 degrees out of my boiler. I would leave at 180 degrees here. I would come back at 160 degrees, and that would be delivering the full BTU to that heat emitter, dropping the BTU, the energy, the heat off in each room, and then bringing it back to the boiler to be recharged. What we're concerned about is having too large of a circulator or having a 3-speed circulator that's always on high, the no callback speed, is that we are now moving the water so fast through this pipe that will shrink the delta T, which means we're delivering the BTU back to the boiler instead of to the heat emitters. Our goal, when we pay for natural gas, when we pay for oil, we want to use that oil to deliver heat to the home. The boiler is generating the heat. I want the heat to come out of the boiler, go out to the heat emitter. I want to kick that BTU off in the space I want to heat, and I want it to come back to the boiler cooler, 20 degrees cooler, so that I can re-energize it and send it back out. That tells me I'm utilizing the heat energy within that water, and I'm going to be comfortable within my home. If I have too large a circulator, I'm going to send the water out so fast, it's going to come back. I may only have a 5, 7, 10 degree delta T, which means now I'm delivering all that heat energy back to my boiler. I'm going to cause my boiler to short cycle. So I'm going to have a lot of startups and shutdowns. And again, that wears out them components. It elevates your fuel cost. So I hope that answers, I think it was Ray's question.
Yes.
Any other ones, Jim?
Well, I think you're going to address this as you go along, but a question came from Keith about turning off the water coming into the system once everything is started up.
Yeah, so we're going to talk, we're going to go through boiler components here very shortly. So we will absolutely positively talk about that and address that, because we want to make sure that everyone is up to speed as to what we're doing there. Okay, so this is a typical cast iron boiler piping system, and we're going to jump right into those components as we speak. So this would be our supply header. This would simulate our supply header. All right, we'll call this a typical cast iron boiler, direct piping out and back. So we leave the boiler, we come out of the boiler, and we go to a low water cutoff. So this is a low water cutoff. It could be 24 volt, it could be 120 volts, whatever your preference is. Some of the goals here with the low water cutoffs, and most inspectors want to see a product with a test button. So how this works, this rod basically goes through and touches the water. This creates a ground through the minerals in the water, and that's what allows this to say, yes, there's water here, and yes, I am working. It allows this to stay lit. What happens is when, hang on one second, we just got another attendee in, there we go. When the water falls below this level, I lose that continuity, and that shuts my low water cutoff down, which in turn shuts down my boiler. This probe does need to be pulled and cleaned every so often. That's going to depend on your system. Each manufacturer will give you their timeline on cleaning the probe. Another key feature here is when you insert this 3/4 brass rod into your black iron pipe, make sure of the depth. We want, if this is touching the backside of the black iron pipe, I will never shut off for low water cutoff because I've created continuity to the pipe. So when you're installing this, you want to check your insertion depth. We want to make sure that this is no way, no how can touch the iron pipe and create that continuity. And to prove that out is you can turn the boiler on electrically, drain the water down, a little bit, and this will come on and it will shut the boiler off. So you got a test light here, so you can always push the test button to make sure that the low water is working. But again, it could be 120 volt, 24 volt. Again, there's nobody that dictates that. That's going to be your preference. And that's going to be whatever it is you like. So we leave there, we come up our riser pipe, and we come across and we get to this point right here. This is what's called the 4900 Taco air separator. Inside of here is a stainless steel fence. Inside of that stainless steel fence, there are stainless steel rings. These are called Paul rings. And what that does is as the water comes through, it will take the air and it will break it up into smaller particles. It will send it up into the top of the exchanger or separator, into the separator, and it will expel them from the system. This upper portion is used on Taco air separators up through 8-inch. So it tells you how robust of a product this is. This was a commercial product that they brought down into the residential world. So very robust. Couple of key features here. No minimum distance from the elbow to the air separator. That's important as these boilers get smaller and smaller and our mechanical rooms get smaller and smaller. We're always pressed for space. If you're used to the old cast iron versions, which are still out there and still being installed, you need a minimum of 18 inches to the cast iron separator. That way the air has the ability to get back up to the top of the pipe so the air scoop can grab it and expel it from the system. Using these air separators, especially if you're doing any type of condensing boilers, it's a must because this eliminates air down to 10 microns. Another nice feature here is these Paul rings will not be affected by antifreeze. They're stainless steel. We call this right here the point of no pressure drop. So we have our air separator. Right here we have a diaphragm tank, and off of this pipe here we have a feeder backflow. So it's a feeder backflow. This is the feed side. One of the great features of this 3450 is it's replaceable. If you have a problem in the field, you don't have to remove the body necessarily. You can just pull out the feed side of it and replace it. So how this works, there's a little gauge right here, and you can rotate that gauge to any position you need so you can view it from the front of the boiler. There's a little black knob here. You loosen this black knob, and then you'll rotate this green knob, and that's how you adjust your pressure within your system. Okay, the old what I call the old purge dance, when you used to take the fast fill valve and put it to the open position, and you're trying to purge out a heat circuit, and you don't get back in time, you blow the relief valve off. Here, if I elevate this up to a higher pressure, let's call it 25, 26 psi, I elevate it up there, I lock it in position, I push the button, it will fill to 26 or 25 psi. It will not overfill. Now, there is one downside. You are not going to get a full force of water like you would a full 100% bypass. This will feed a little bit slower than your typical fast fill valve. Jim, you had a question?
Yeah, just quick back to the low water cutoff.
Yep.
About putting either Teflon tape or Teflon paste
Yeah.
on the threads.
Yeah, so usually your first two threads, you don't really want anything on your first two threads. But look at the manufacturer, whichever manufacturer it is, look at the manufacturer. They're going to give you some guidelines as to what they want you to use. But usually the rule is the first couple of threads, you don't put anything on the first couple of threads because that's part of the connection point to complete that ground. This is a feeder backflow. So on the backside, we have a backflow preventer. So just by removing this cap, that gets me into my backflow. Backflow has a screen internally. There's also a check valve internally. So if you shut the water off, it won't drain the system. But here you go. This is a backflow preventer. So the question earlier was, about shutting the system off. I think if you go through and look at just about every manufacturer's guidelines, they'll tell you that after the system is full and charged, you would shut the valve off in front of the feed valve, the boiler pressure reducing valve, and eliminate it from the street pressure. And you have a low water cutoff now in place. So if you end up with a low water situation, it would be the job of the low water cutoff to shut the system down. So that is what most manufacturers will tell you to do. We don't necessarily see that a lot in the field, but that is the recommendation. Okay, so this is the point of no pressure drop, and we have our feeder, our expansion tank. That comes out of the box. The feeder comes out of the box at 12 psi. Right down here is my Schrader valve. My air pressure is at 12 psi, and that should be a happy system. And we'll talk about static pressure in a system in week 3. So we leave this point of no pressure drop. We have the inlet side of the circulator, and I keep referring to them as circulators. They are circulators. We always call them pumps in our industry, but this has to be wet in order to move water. And all this really does is create a pressure differential. So our goal is to keep the backside of the circulator at the system pressure. So call that 12. When we turn the circulator on, we want a positive 4 or 5 psi change on the positive side of the circulator. So back here, we're going to remain at 12 because this is the point of no pressure drop. I'm going to turn this circulator on. This side of the circulator, the inlet side, will stay at 12. We're going to come through the circulator. Our impeller is going to start to rotate. We're going to start to kick that water up, and we're going to increase to maybe 14 or 15 psi, 16 psi, 17 psi, whatever it is, depends on the circulator. But 4 to 5 psi would be the number. So call it 16, 17 psi exiting the circulator. And we're going to use that additional pressure to overcome the friction of the pipe that's going out to the heat emitter and coming all the way back to the boiler. So that's one part of the equation when we said a little while ago in the beginning that we were going to teach you how to size circulators. 2 things we need to size circulators. We need to understand the head which is the friction loss of that pipe, and we need to understand the flow. So once we understand those two items, we'll take you to a circulator chart and we'll start to size circulators properly. So we get the proper flow rate, the proper pressure increase, and the proper delta T across the system. Jim, any questions? Is that making sense to everybody?
Yeah, there was a question about, do I need another check valve downstream from the backflow preventer?
That will depend on local jurisdiction. We do make boiler kits, and in New Jersey, the inspectors like to see brass. So all of the boiler kits that we put together, we have brass T's, brass nipples, and ball valves going to the pressure reducing valve on a boiler system. So whether we put together a cast iron system like this or even a condensing system, we put full boiler kits together so it can simplify a contractor's life in the field, but we do install brass there. Okay, so again, it doesn't matter if it's cast iron, it doesn't matter if it's condensing, it doesn't matter if it's primary, secondary, or standard piping. These components are still going to be located kind of in the same location on primary, secondary. Our air scoop will be down on, I'm going to call it the system circuit and the boiler circuit. You know, usually it's referred to as a primary circuit or a secondary circuit, but a lot of people get that mixed up. So we refer to it as a boiler circuit and a system circuit, and all of our components that you see here would be on the system circuit portion of the install. So TACO has a whole array of ECM circulators, and we just want to make sure that you guys are aware of what is available to you. So on the plumbing side, there is a 006E3. So that would be for any type of recirculation that you may have. And TACO's done a really nice job on the boxes of identifying distances and what that type product can be applied to. We also have a 007. The 007 is now starting to be instituted on majority of the boilers that are coming out, whether it's Wall-McLean, Burnham, ECR. You know, there's a whole list of different manufacturers that have now gone from the typical 007, the AC version, to the new ECM version. And these are available in either a two-way or a four-way flanged type system. If you are very particular with your install and you always want to be able to read the tag, there are 4 Allen head keys right here, screws that you would just take out. Don't remove the motor, don't pull the cartridge out. Just remove the 4 Allen keys, rotate it to the position you want it in, and then put the 4 Allen keys back in. There's a gasket in there that's kind of in a groove, and it's very difficult to get it back in if you pull the motor out. Okay, some of the features of these new ECM style series, they got a whole family of them now. Super easy to wire. This unplugs. You got top and bottom. You can wire it into top and bottom. This unplugs. We give you the, you know, the white and the black, and we only give you a white and a black. So this whole ECM series, the motors are double insulated, so they do not need a ground. So you just have 2 wires right inside there, and the cover plate goes on, and you can put your wire nuts in here, and it's a nice, neat fit. So we have the 007E. Again, this is becoming the norm on OEM boilers. We've added an LED light. If you haven't seen one of these in the field yet, we've added an LED light. This will be running in the orange mode most of its life. Depending on what circulator you're dealing with, there are different colors that you will see. So orange is the 007, that's heating mode. Red is telling you that the circulator shut off for some reason. And white will tell you that the circulator has the ability to do a couple of different things. I have another 007 that I can show you here in a little bit. White is either it's in air purge mode or it is in what's called sure start mode. And we'll go through that with you here shortly. We also have, and when I was out in the field, I wish I had this on my van way back when. It's a 4-bolt. We have a 4-bolt or a 2-bolt 0015 E3. So you have the ability now for 3 different speeds and to overcome, whatever type of application you're in. This is more flexible. It gives you a wider window of operation. So another one in the ECM family. For the guys that really like to go above and beyond, this is a 0018E. This has Bluetooth capability. So if you truly want to dial a system in perfectly, you can connect to this with your phone through Bluetooth. You will see the exact head and flow of this circulator in the system at that moment. It's live. So really neat. Again, all the different settings, so you can dial this circulator into the exact flow rate and the exact head that you need to support that system. Still in the Taco ECM family, we have a 0026E coming out with stainless steel and cast iron. That 0018E I just showed you, we'll have a stainless steel version of that coming. And then we go all the way up to the big brother of all of these, the 0034E. And we have a stainless steel version and a cast iron version. The 26 and the 34E have the ability to talk to a 0 to 10 volt boiler. And by sending a 0 to 10 volt signal to the circulator, it will ramp up and down based upon what the boiler is telling it to do. We have typical, your delta P, like a typical AC circulator. Couple settings there where it'll modulate, and then we have the high setting where it'll be on constant. And we also have what we call active adapt, which if you have a constant circulation system, active adapt may be a good choice for you, where you may have a Danfoss valve opening and closing. So that's all part of the ECM family. We go further than that with the ECM family. We go all the way up to, if you're familiar with Taco circulators, we have the VR series, which is kind of like that light commercial. And then we go all the way up to the 1900 series on the commercial side. We're also the only ones in the game right now with a Delta T circulator for residential type applications. So we give you a Delta T circulator, which has the ability to look at the supply temperature and the return temperature, and it will vary its speed based upon the supply and return temperature. So if you want a 20-degree Delta T, that's where it comes out of the box. You don't have to set anything up. You just put your supply sensor with a piece of insulation over it, your return sensor with a piece of insulation over it, and that circulator will modulate up and down until we achieve a 20-degree Delta T, and it will run at a 20-degree Delta T. As zones open and close, it will ramp up and down to support that heat demand within the home. So Taco has a whole array of ECM circulators out there. We still have all of our standard AC circulators. They're not going anywhere. We're going to introduce a couple of enhanced versions here in the near future on the AC side of the marketplace. So stay tuned for those. And I just wanted to run you through. This is a 007E. And this is the position it would be in. I've took this 007E and basically we've disassembled it. Okay, we took the whole housing off of it. We want to explain how these wet rotor circulators work. Okay, so when you first put water into a system, this goes across the board for all of our double O's. When you first put water into a system, water goes in through the eye. It goes in through the eye and it fills up this area right here. So if you've ever seen a 007, well, now you're seeing a 007E. This fills up with water and these become a water-cooled circulator. So the two main things that kill circulators are black iron oxide and air. So because Taco is an American company and they understand the water conditions here, these are built right in Rhode Island. So you're supporting our local economy by buying Taco. This is what we call a biobarrier. That biobarrier is located right here. So as the water comes in the eye, it has to go through this biobarrier. Biobarrier, what is that? Black iron oxide. Black iron oxide is metallic. This rotor is a permanent magnet because it is an ECM driven circulator. So we're the only ones on the market with the biobarrier. So if you have metallic items floating around within your system, which every system does, we want to catch that with the biobarrier before it gets into the magnet, because this is a permanent magnet. It's not like an AC circulator where we have to generate magnetism by rotating the motor. We have a permanent magnet, so there's no slippage or anything else. So it rotates. So this goes into the housing, and this is, and you'll see this snap in pretty quick because of the magnet, right? I'm letting that go. It snaps in because of the permanent magnet. So our water comes in, goes through the biobarrier, fills up that housing. That becomes our water-cooled system. These circulators run extremely quiet, and the temperature compared to a 007, this is much cooler than the temperature you would feel on the outside of a 007. So how this works, if I plug this in, it will start to rotate. And if it's in a heat mode, I will have an orange light. Then what I can do is I can grab the impeller and I can stop that rotation, and it will recognize that the rotor has stopped turning. And the light will start flashing white, and it will go into what we call a sure start mode. It will actually take the impeller and it will rotate it back and forth, back and forth, back and forth. It thinks that there may be something attached to the magnet and it wants to break it loose. So it will start to rotate it back and forth. If it has the ability to break it loose, you will never get the service call. The homeowner probably won't know that it happened. You probably will never know that it happened, but this circulator just saved you a service call. Okay. The other feature, let's say you just did a boiler install and you put all new 007Es on there and one heat circuit went airbound. The light will start to flash white. The circulator will ramp up to about 5,000 RPM, 5,000, 6,000 RPM, and it will come down. And it will continually do that until it thinks it's going to hurt itself, or 100 cycles. And if it moves the air pocket, you don't get a service call. If it does not move the air pocket and it realizes that it's not going to overcome the problem, this light will turn red. It will shut the circulator off. You will get the service call. You'll go there. You'll purge out that heat circuit. You'll power this 007 down, power it back up, and it will go right back into operation mode. If this were a typical AC driven circulator, brand X, Y, or Z, it would have ran dry and it would have cooked itself. So there are some serious advantages to the ECM side of our circulator world. So we're going to plug this in and you'll see it's flashing, right? Now it's orange, it's in heat mode, but it's recognizing that there's no tension on the impeller. And you can see it flashing white. And I'm going to put it right close to the speaker. I want you to hear it. You can hear it ramping up and ramping down. That's trying to purge the air out because it doesn't feel resistance on the impeller. So now what I'm going to do is I'm going to stop it. And it's flashing white. You're going to see my hand here start to shake. See my hand start to shake? And you can hear it. That's shaking back and forth, back and forth, back and forth at a very rapid rate of speed to try to break whatever is holding the impeller from turning. So this will self-diagnose and try to correct itself in the field and try to save you a service call. So we're going to unplug that so we don't completely cook it. But that's one of the benefits of going to the E-Series circulators. And the reason I went through that in such depth is because, like I said, Burnham, Weil-McLean, ECR, I think there's like 4 other manufacturers that have signed on with TACO to have this being their OEM circulator of choice. And then we'll get into the performance curves of the 007E as we get into the sessions going forward and showing you how to size the circulator correctly and everything about whether it's an AC circulator, which is great, we don't care, or whether it's an ECM circulator, that's fine too. Jim, we're just about wrapping it up here. You have any questions?
Well, Ray asked if the biobarrier needs to be cleaned or replaced. My response was it does not.
Okay, on the biobarrier. So just so you guys understand how this works, this is not a filter. And we just want to be clear on that. You're not going to be replacing this in the field. When we take on water through this eye, the water that goes in behind that black iron oxide barrier basically stays in the circulator. This is not a constant flow of water that goes through the circulator, right? So we're not filtering the system with this black iron oxide barrier, with the biobarrier. So we take the initial fill up, we run water through the eye, we fill that chamber. You might get a little bleed by when the circulator is running, but it's not a constant exchange of water. You know, we're not moving 2, 3, 4 gallons a minute through that biobarrier. You know, we might be moving a drop of water through the biobarrier, but no, you would not be changing out that biobarrier. Any other questions?
No, there was a question earlier about getting BTUs for pipe size for 1/2 to 1.25 inches, and I know that will be addressed further along in the program.
Yep, we'll put that in the handouts. We can put that in the handouts for next week.
Then a gentleman, Stephen, was wondering, are these ECM circulators on any of the NTI boilers?
Yes, they are. We're the NTI rep, so yes, we know they're on there. It's actually integral to their TRX boiler. This is the circulator of choice. So just a quick history on TACO's jump into ECM. Going back almost 5 years now, they partnered with a company called TACO Italia. Well, that's what they call it now, TACO Italia. But there was a company called Askell, and Askell has been making ECM circulators since 2002. So TACO partnered with them and eventually purchased them for the circulator side of the business. Askell makes high-end pumps for dishwashers, high-end pumps for wash machines. So they've been in this pump world for forever. That's their business.
Aquariums too.
Yeah, aquariums, right. So they're in the pump business. So TACO basically partnered with them, eventually purchased the circulator side of it. TACO knows the American marketplace, as I said earlier. They incorporated the biobarrier. We have that biobarrier on all of our 00s. So we're familiar with the biobarrier on our 007s and so on down the line. So we incorporated that biobarrier into all of our 00 series. We have gotten the ECM sales numbers up high enough to where these are actually built in Rhode Island now. And it's been a really positive journey for TACO and Wells Darby to go down this ECM road. It may not be the answer for everyone, but the people that are thinking ahead, I don't want to, you know, the biggest advantage to me is saving a service call, but these do run approximately 85% more electrically efficient than a typical AC unit does. The maximum wattage on a 007 would be 44 watts compared to an AC driven circulator would be 80 watts of energy. And we will vary down from there. So, you know, there is some advantages, but to me, it's more from the service side as to why I would go with the ECM version. There is a little bit elevation in cost. We get that, but that's going to be your choice, you know, in the field. We have both and both work extremely well. Any other questions?
No, we're good. I mean, there's questions about where to put the circulator on the system. You know, supplier return the best. We are going to go into that in more depth as we go throughout this program.
We will. Yes, we will.
You know, but yeah, no, we're in good shape.
Okay, so day one, week one, Advanced Hydronics. We apologize for some technical difficulties. Don't forget about, we have HVA Insiders is our site where we post a lot of this information. We do podcasts and everything on there. So HVACinsiders.com. It's directly linked to Wells Darby. You will see a bunch of us on there. So we're trying something new. Again, I apologize for the technical difficulty. Keep your eyes open for a blast from our marketing department with some additional information. And I just want to thank everybody in the room today for getting up really early and trying to get this thing off the ground. We will work from now till next Wednesday to try to correct whatever malfunction. We really appreciate everyone's time and look forward to seeing you next week, 7 a.m. Wednesday morning. Same bat station, same bat studio, same crew of people. Jim DePalma will be your instructor for next week. Thank you very much.
Have the handouts ready.
Take care, everyone.